Good day or good evening everyone. I'm Abdur from Khalifa University. I'm going to present my work with Bashar El-Khasawneh and Cesare Stefanini on a novel reconfigurable hybrid kinematics 5-axis machine tool. Let me start with some background. Large structures are not practical to be moved for machining. In this case, moving the machine is more practical. Hybrid kinematics machines have been used to integrate the advantages of both serial and parallel kinematics machines, including larger workspace and higher stiffness-to-width ratio. For 5-axis machining, 3D-to-R mobility is required. Here, we are proposing a machine which, instead of changing its mobility by reconfiguration, it keeps its mobility unchanged, but it changes its workspace and properties of the workspace to adapt to various positions and sizes of workpieces or structures. Here are some considerations of the design of the machine. First, mobility. The manipulator should provide 3D-to-R mobility to perform 5-axis machining. Second, reconfigurability. The machine should be able to be reconfigured to adapt to variation of workpiece size, geometry, machining direction, and reach. Third, modularity. The 3D-to-R mechanism, which consists of 2 modules, should be able to be transformed to 3D mechanism by modularity. And this is also a kind of reconfigurability. Fourth, practicality and cost. In all of the configurations of the machine, the placement of the actuators should not be changed so that it results in a minimum number of actuators. And the fifth, extensibility to a mobile robot. Because the machine is going to be used as a mobile robot for machining, then it should be able to be easily extended or integrated with a mobile base. To achieve this, there are some possible distributions of degrees of freedom as shown in this table. First, it can be a combination between a 3DOF parallel mechanism with a 2DOF serial or parallel mechanism, and it can also be a combination between a 4DOF parallel mechanism with a 1DOF serial mechanism. After comparing all the options, we selected a combination of 3T parallel mechanism with a 2R parallel mechanism. This provides some advantages. First, the 2 modules provide clear separation between translations and rotations so that each module does not have mixed degrees of freedom. And then the manipulator can be transformed from 5-axis to 3-axis by modularity. And then the use of parallel mechanisms for the second module, which is the 2R module, is expected to offer the advantages of parallel mechanism. This is the schematic of the proposed reconfigurable hybrid kinematics machine. The machine is mounted on a base structure shown in gray here, and then on top of the base structure we mount a reconfigurable frame shown in brown. This reconfigurable frame can change its angle theta, and then we mount the 3T mechanism on this reconfigurable frame. The reconfiguration of this 3T mechanism is achieved by locking or reconfiguring some of the joints. On the right hand side, we can see the reconfiguration of the 3T mechanism. One of the topology is an orthogonal topology, and the other topologies are non-orthogonal topologies. This is one of the main distinction of this machine, which is providing both orthogonal and non-orthogonal configurations. And then we connect a parallel 2R mechanism to the 3T mechanism. Now let's see the first topology, which is the orthogonal topology. This topology has a symmetric 3PR-PR joint topology, and the workspace is a box. This is basically the largest workspace compared to those of the other topologies. This topology consists of three configurations. Configuration 1 is a retracted orthogonal configuration, which is suitable for stationary machining inside the bit structure. Configuration 2 is an extended orthogonal configuration, which is suitable for mobile front machining with limited height workpiece. Configuration 3 is good for front machining. This is achieved by tilting the moving frame or the reconfigurable frame to the front. This is suitable for front machining in which the height of the workpiece is more than the bit structure of the machine. And on the right hand side we can see a physical model of the machine at an orthogonal configuration. This physical model was built to verify the mobility of the machine. This is some animation of topology 1 or the orthogonal topology. On the left, this is the configurations 1 and 2. And then on the right, this is configuration 3, where we tilt the reconfigurable frame to the front. And then the next are topologies 2 and 3, which are non-orthogonal topologies. Both topologies have an angle theta between 90 degrees to 180 degrees. The topology 2 or configuration 4 has the joint topology of 2 PR-PR, 1 PR-PU as shown on the left. And then topology 3 or configuration 5 has the joint topology of either 1 PRP, 2 PRPU, or 1 PRP, 1 PRPS, 1 PRPU as shown in the middle. Both the topologies have the workspace as shown on the right hand side, which is shown from the side view, normal to a plane made by limb 2 and limb 3. The shape of this side view of the workspace is like a diamond, which is dictated by the angle theta and also the motion range of the proximal P joints. This is some animations of both the topologies. On the left hand side, we can see topology 2 or configuration 4. And then on the right hand side, topology 3 or configuration 5. They look similar, but the difference, as I said, is the joint topologies. And the last topology is topology 4, which is also a non-orthogonal topology. The angle theta in this topology can be either between 90 degrees to 180 degrees, which is called configuration 6, or equal to 180 degrees, which is called configuration 7, or more than 180 degrees, which is called configuration 8. The joint topology in all of these configurations is the same. Limb 1 is PRP, and limbs 2 and 3 have two possible joint topologies depending on the placement of actuators, as I will describe very soon. The first possible topology is 2 PUU or 1 PUS 1 PUU, and the second possible joint topology is 2 UPU or 1 UPS 1 UPU. This topology, which is topology 4, is suitable for mobile front machining with tall workpiece. This is some pictures of the physical model at some non-orthogonal configurations. On the left is the physical model at configuration 6, and in the middle is at configuration 7, and on the right hand side at configuration 8. And these are some animations of the three configurations in topology 4. On the left, This is configuration 6. And then in the middle is configuration 7. And then on the right is configuration 8. As I said, there are two possible placement of actuators. We can place the actuators either at the proximal P joints as shown on the left hand side, or we can also put the actuators at the intermediate P joints as shown on the right hand side. The topologies 1, 2, and 3 do not change by the different placements of actuators. Only the placement of actuators are different as indicated by the underlined letters, which means the actuated joints. Only in topology 4, the placement of actuators results in the change of the joint topologies. If we actuate the proximal P joints, topology 4 has this topology as shown on the table, the last row. And when we actuate the intermediate P joints, the joint topology is as shown on the right side of the last row of the table. Now, one of the main consequences of the placement of actuators is the workspace. In topologies 1, 2, and 3, the placement of actuators do not change the workspaces. But in topology 4, there is difference in the workspaces due to the placements of the actuators. As we can see, in topology 4, when we actuate the proximal P joints, the workspace is much smaller than if we actuate the intermediate P joints, where we have larger workspace as shown on the right hand side. Because of this, we decide to use the actuators, or to place the actuators at the intermediate P joints. And finally, this is the topology of the 2R parallel mechanism. After comparing some topology candidates, we selected an over-constrained decoupled 2R parallel mechanism having RRR topology, where all the joints are revolute joints, and we actuate two revolute joints. This was firstly proposed by Professor Goslin and Karen. What we did with this is enhancing its stiffness by using double bar links as shown on the right hand side, where we can see the green and yellow links are double links. This is enhancing the stiffness of the links, although we need to use more roller bearings in the physical implementation. And the second thing we did is optimizing the motion range to avoid collisions during the motion, and then we come up with an optimized design which is capable to tilt in the range of minus 90 to positive 90 degrees about two axes, let's say X and Y axis. So the range is 180 degrees, which is very, very good. Thank you.